Hello, in this video, we're going to analyze the big O of a more complex algorithm, binary search. So this is a version of binary search from the 3A that I taught. Even if you didn't take 3A with me, this whatever binary search that you study should be uh, very similar to this version, if not exactly the same. So basically, given a list and a key, the binary search is just is going to look up the key in the list, and if it finds it, it will return the index of the key, and if not, it will return none. The important thing to remember about binary search, obviously, is that the list must be sorted for it to work. Okay, so what is the big O of this algorithm? Let's first do an estimate, and let's do it with a little example. That let's say we're given a list that has 64 elements. In binary search, as you hopefully remember, it actually calls itself, right? So with 64 elements, and in the first round, when the first time the binary search is called, how many of the elements are eliminated? Well, half of them, right? Because uh, every time we look at the middle of the list, and if that is not the key, then depending on whether it's that element is bigger than or smaller than the key, we either go to the left half of the list or the right half of the list. So every time half of the list is eliminated. So again, first time in a 64 element list, 32 of them are eliminated. In the second round, then by the same token, 16 of the 32 that are left are eliminated, and then it goes on and on until when it terminates. It terminates it terminates when the list becomes empty. Okay, so if we kind of uh, uh, write a table that on the first column is just the round number, and then the second column is the number of elements remaining in the list. So initially, initially we have 64 elements. After round 1, we have 32. After round 2, we have 16, and so on and so forth, until round 6, we have 1, and then round 7, we have nothing, right? So this is it's going to take 6 rounds, 6 or 7 rounds. I'm probably off by 1 here. 6 or 7 rounds to find the answer for 64 elements. So, okay, so let's double the input size to 128 elements. How many rounds do you think it's going to take to search for a key in a list of 128 elements? Well, it should take just one more round than before, right? Because from 128, we just take one call to binary search, and we'll eliminate half of the list, so 64. So when you think about this, is quite remarkable, right? Because we double the size of the input, but we added only one more call to binary search. So this is actually good, very good. Now let's actually do this, do another table, but in a slightly different way. So in this table, on the first column is just the number of elements in the list. Right? And in this column is the number of rounds for a binary search to find the key. So we already know that for 128 elements, it takes 7 rounds. For 64 elements, half of that, it takes 6 rounds. So hopefully it shouldn't take a whole lot of work to derive the rest of the numbers here. And the rest of the number is really kind of 7, 6, and for 32, it's going to be 1 less than 64, right? 5, 4, 3, 2, 1, until the simplest case. So when you look at this these two columns and remember what our goal is. Our goal is, given the size of the input, which is the number of elements in the list, we're trying to estimate the amount of time that it takes to find the key using binary search. And the time is kind of proportional to the number of rounds or number of calls, number of recursive calls to binary search. Right? So what kind of function is this number of rounds in terms of the number of elements? So for those of you who remember your math, this function is really just log of base 2. So if you look at, let's say, pick an example, the one we're familiar with, right? 6. 6 is really the log of base 2 to the 64, right? And so it's 7, etc. The base case also kind of, check out, right? So this is what's called the logarithmic growth. So in general, for binary search, if the number of elements in the list is n, then it takes kind of on the order of n, the order of log base 2 n comparison to, or recursive calls to find the key, right? And so binary search is really is O of log n. Now you notice I kind of eliminate the base 2 here because we're usually not concerned about the exact base. And most of the time the base is 2 because modern computers are binary systems, and in particular for binary search, we eliminate half of the list every time. So that is really kind of a hallmark of something that is a log of base 2. Okay, so we usually just say log of n, O of log of n. So if we look at some really big numbers, such as 1 million, that's roughly just 20 recursive calls or comparisons. So that is a very fast search algorithm, especially when you compare to the linear search, which linear search is just linear. So it's O of n. That's very, very slow. Okay, so that's kind of, just looking at how binary search works and come up with kind of an estimate of the big O. Now, if for those of you who are more mathematically inclined, you want some more rigorous analysis using math, we can do that as well. Now, so let's assume T of n is the runtime of the binary search, right? For an input of n, that's the definitions that we've been using, right? So we know for every call to binary search, there's some constant amount of work, right? Because we have to do at least these checks and calculate the middle and at least check the key against the element in the middle. So all of this, they're not in a loop, so they're constant amount of work. So let's denote that by the small c, constant amount of work. And then we know after this bunch of work, binary search, assuming it's not done, and again, we're looking for the worst case here, so this is not done, we will call binary search recursively. We either go to the left side or the right side of the middle. And when we recursively call binary search, we give this new incarnation of binary search half of the list. Okay, so that's that time, the recursive binary call, then the time it takes, it would be Tn over 2. Right? Remember, T of n is the entire list. Right? So the recursive call is half of the list. That's why it's T of n over 2. All right? So then what is T of half of n? Well, if we plug in half n over 2 into this n here, then we will have n over 2 over 2, which is n over 4. Right? So, okay, next step, putting these two things together. what we're going to have is, we start with, again, t of n is Tn over 2 plus c, right? T of n over 2 is T of n over 4 plus another c, as we just saw here. So that we come to this line, and then we can kind of take out the parentheses and we add the 2c together. So we have 2c here. Okay, we can keep doing this. What is Tn over 4? Well, it comes out to be T of n over 8 plus a c. And again, we take out the parentheses. We're left with T of n over 8 plus, now we have 3 c's. Okay, where does this lead us? Where does this end? It ends when we get to T of 1, right? When we only have one element left. So we know we're going to end with T when the size of the list reaches 1, so T of 1. Now the question is, what is the number in front of C? Right? Okay, how do we find that? Well, first, let's kind of rewrite this thing, clean it up a little bit. And then we're going to start seeing some patterns, hopefully. So we're going to rewrite these 4s, 8s, and even 2s in terms of power of 2. So 4 is the 2 to the 2 power, 2 square. And then 8 is 2 cube, and so on and so forth, right? And one thing to notice is that this power here is exactly the number that is in front of C. So that is one observation. And then another thing we want to rewrite is we want to rewrite this 1 as close to these n over some number as possible. So 1 is going to be n over n, right? Okay, but this n is over n. What about n? We still want this n to look like 2 to some power, right? But we don't know exactly what the power is yet. But we can write it as 2 to the some power, and we're going to P, we're going to denote that power as P. P is unknown right now. That's fine, but we can solve it. But also note that just as everything else, this power is the same as the number in front of the C. So P is going to be the number P in front of C. So all that we have to do now is to solve for P. Okay? And we know that n over 2 to the pth power is 1, right? That's what we started with here. So we can write that 1 is equal to n over 2 to the pth power. Okay, and if you go through the math here, I'm not going to just describe every line, but hopefully if you remember your math, this is how it works. And then it will come out to be P is a log base of 2 of n. Okay, so then we're going to write this as, we're going to put this back. So this term is T of 1, so we're going to say T of 1. And now we know P is log of base 2 of n. So P of, well, log of base 2 of n. And then we end up with this little formula here. Now T of 1, we know how long that's going to take. If the list is empty, it's not going to do any more recursive call, right? So there's no more repetition when we reach the escape or the terminating case. So T of 1, that is some sort of constant. And like we said before, constant we're not concerned with constant in big O. So that's that. We can eliminate this term. Now, this C here, we also said it was a constant cost. And remember where it comes from. This C is really, again, it's the kind of the same amount of fixed cost that's before the recursive call. So again, in big O, we're not concerned about the scaling factor in front of any functions that involve with n. So we can eliminate the C as well. So we are left with, in terms of big O, is just log of base 2 of n. And that is, like we said before, is the same as log of n as far as big O is concerned. And that's exactly what we arrived at when we were doing the estimation previously. So that's good. Both our mathematical analysis as well as our estimation match each other. Okay, so the final thing that I would show you is that, okay, now we know in theory the performance of binary search. We should actually verify it. Okay, and the way I'm going to do this is I'm going to vary the size of the input, right? So I'm going to take 2 to the nth power, and these n's are going to, these are the numbers that work on my machine. So starting at 2 to the 10th power to 2 to the 28th or 27th power. And so the actual size is kind of 1,000, 2,000, double every time, all the way up to, I think this is over 100 million. Okay, and I'm going to loop over the sizes. I'm going to generate just a sequence of numbers, a list of sequence of numbers, all from 0 all the way up to the size. And remember, they have to be sorted, right, for binary search to work. And when I run it, I see that this is actually the line of code that actually took the most time. It takes a while to generate a list of 100 million items, right? And the next thing is, we pick a key. So I pick a key that is the size divided by 3. So it's kind of, in a non-part of 2 position. So it's somewhere in the odd place in the list. So hopefully, it will pretty much exhaust all the recursive call of binary search before it finds this key. And anyway, I use the same, performance counter thing, and just surround the binary search call with 2 performance counter. And I'm going to just print out the size and the duration. And I actually do have the code here. I'm not going to run it because it takes a bit of time. So you should really try to run this on your machine and verify the result. But here is what I had from one of my runs. So again, this column is just a size of the input list, and this is the time. And I actually graph it out as well. So on the y-axis is the duration, and then on the x-axis is the n, or the size. So if you look at the shape of this thing, and if you remember how a log function looks like, this kind of looks more or less like a log function. Obviously, there are little kinks and things here that is kind of expected because this runs on a real hardware. There are going to be variations, small variations on actual machines. Now, of all these numbers here, there is one number that is a little bit off. So I don't know if you can see it. If you want to give it a try, pause the video, try to find the odd number, the weird number. Now, what it is this last number here. It's really an outlier because if you see it, look at all these numbers, the way they progress is they kind of increase, but very slowly. Right? But then this large number is all of a sudden is almost 4 times as big as the one before it. And I actually did not include this number as part of this plot because it would then, this plot would kind of take off, have a line that takes off at the end. Okay, the reason that I think this happens is that things are going to go kind of weird when the list kind of reaches a certain size. So on my machine, this happens with the last list, which has like 134 million numbers. That takes up a lot of memory. So I think at that point, my machine is trying to find more memory, and it's like couldn't really find it in the RAM. So it's starting to kind of do this thing called, swapping the memory out to disk. And if you don't know the difference, just know that when you're swapping things out to disk, this is a lot more slower than the RAM. So when the computers start doing that, things are going to slow down by a lot. And I believe that's what happens. So this kind of helps to illustrate 2 points. One is in the real world, when you want to do measurements, it's actually not that simple. There are all sorts of factors that can come in and change your numbers. Okay, and then another thing is, I think we said at the beginning that when we measure the performance of an algorithm, we should measure both the time and space, although in this class we focus more on time. So this is the case where we see that the space requirement of an algorithm is also going to affect how the algorithm is going to perform. Okay. So one more thing that I want to say is kind of following the same thought from the previous slide, is that if you do run this on your machine, your number are going to probably, most likely, it's going to look different from mine, right? And could be quite different. So that depends on, whether your CPU is more powerful than mine, probably, whether you have more RAM or less RAM, and whether you're on Windows or Mac, so on and so forth. So now, even on the same machine, like on my machine, if I run this multiple times, each run is going to produce slightly different numbers. Sometimes they are very different numbers, but most of the time they should be just small differences if we run the same performance measurement. It's just, as we just saw, there are just so many things that can potentially kick in. There's so many factors that can affect the performance. A lot of things that we don't necessarily see if we're not aware of how a particular piece of hardware, a particular piece of software or operating system work. So when we do performance measurements, we usually do multiple runs and maybe do some statistical analysis, sometimes simple, sometimes very complicated over multiple results. Okay. Anyway, so hopefully that's helpful. And just kind of as a summary, when we study the algorithm's performance, what we can do, and sometimes we should or must do, is we can intuitively try to figure out how it's going to perform, right? So if we know how an algorithm works, we probably have a sense of how it's going to perform. And this is very often in the industry. This is how you're going to work. It's just to get an idea, get an estimate of how well whatever the code that you write is going to perform. Now, if you're more in the academia, into research and stuff, then you would use the math to kind of derive its big O more rigorously, like what we have done. And then finally, both of these are on paper. You really should verify the estimated big O by running some real experiments. And as we saw, when we run real code in the real world, things may not be exactly what we expected. But it's okay, we can, figure it out. But it's important to verify your theory with actual runs.